In this nugget, we'll take a look at some compelling reasons for why we might change an IP address inside of a layer 3 packet, and this process is known as network address translation, or NAT. As we learned in the IPv4 subnetting course, we have private IP address spaces that we can use internally inside of our companies. And that's great. That's what we're using right here. For example, here on this network at our company, we are using the 10 network. Specifically, we're using 10.1.0.0/16. We're doing custom subnetting. And we're using this first 16 bits to represent the network, and the last two octets are available to identify individual hosts on this network. So let's say this computer right here is Bob, and Bob's sitting at his computer. It's on the 10.1 network, and Bob decides, hey, you know what? I'm going to go out to the internet. So Bob opens up a browser and goes to www.google.com. And one of the very first things that's going to happen is DNS, Domain Name System, is going to resolve the name of google.com to an IP address. So Bob's computer makes a DNS request, gets a DNS response. And let's say for our example that DNS resolves google.com to the address of 72.195.166.22. The next thing Bob's computer does is it asks itself, is that IP address right there, is that on the same local network as I am? And the way Bob's computer makes that decision, it looks at the network address that it's currently on, which is 10.1, and it compares it to the first two octets, in this case, of the IP address it's trying to reach. And if the network portion of Bob's address does not match the destination, Bob knows two things. Number one, it's not local. It's not on my local network. And secondly, Bob is going to need the help of its default gateway. And so for our purposes, let's say that the router 1 is the default gateway for the 10.1 subnet, and that the router 1's host address ends in .1. So Bob's computer would forward a packet to 72.195.166.22. And that would be the layer 3 IP header address where it was going. The source address would be Bob's computer. But at layer 2, what Bob would do, Bob would forward that to the layer 2 address of its default gateway. And if Bob's computer did not yet know the layer 2 address of the default gateway, it would use an ARP request, ARP, Address Resolution Protocol, to determine what the layer 2 address is that corresponds to the default gateway of .1. And that would be sent into the network. Now the switch, which is a layer 2 device, would make a forwarding decision based on that layer 2 information. The switch would have learned the port where the router lives based on the MAC address, and the switch would forward that information at layer 2 only to the port that needed it. So the internal server, switch number 1, and all the other devices wouldn't have to be bothered by receiving and looking at this layer 2 frame. So then the router gets the frame, and because when it receives the frame, it looks at the layer 2 address for the destination and says, hey, that's me, and it de-encapsulates that, and it starts looking at the higher layers. Once it looks at layer 3, the router says, the IP address that this is destined to is 72.195.166.22, and furthermore, says the router, that's not me. So I'm not going to continue de-encapsulating this packet, but what I will do, because I'm a router and I know how to forward this packet in the direction of where it needs to go, I will continue forwarding this packet to its destination or in the direction of its destination. So to help accomplish that, router 1 has something called a routing table. So in the routing table, if it knew that to forward a packet to 72.195.166.22, it needed to send it over to the firewall, what the router would do, it would take the packet at layer 3 and it would re-encapsulate it at layer 2 with the layer 2 address of the firewall. And if the router did not yet know the layer 2 address of the firewall, it would go ahead and ARP. On an Ethernet network, it would ARP to discover the layer 2 address for that next hop. And when this firewall receives it, if it's also acting as a layer 3 device, it would look at that layer 2 frame, say, hey, that's me. It would de-encapsulate up to layer 3, look at the IP destination address and say, hey, that's not me, but I do know how to route in that direction. I can forward this packet. So the firewall also has a routing table that it can refer to if it's acting at layer 3, and then it can re-encapsulate it at layer 2 with the correct layer 2 address of R2. So when R2 receives that frame, it de-encapsulates it and says, hey, the IP address this is going to is 72.195.166.22. That's not me, so I'm not going to continue de-encapsulating it and see what's in the payload, but what I can do is I can forward it in the direction it needs to go. And it would also then re-encapsulate and forward based on its routing table. Now, that's kind of a big picture summary of what happens, but in this nugget, I'd like to chat with you specifically about a major problem. And here's the major problem. The service provider right here is not, when it's forwarding packets on the internet, the public internet, it is not going to allow packets that are sourced from a private IP address space, such as 10 anything. And the service provider also will not forward packets if they are destined to a private IP address space. Those are not considered to be routable over the public internet, because it is likely that there are millions of companies and entities that are using that private IP address space. So it's not routable over the internet. So how do we get Bob at Computer 2, who has a source IP address that begins with a 10 network, how do we get his packet successfully routed over the internet? And the answer is, my friend, we are going to lie about the IP address that Bob is using. And this lying process is referred to as network address translation, or NAT. So to implement NAT here on R2, what we could do is assign R2 a pool of IP addresses. Let's say we have 23.1.2.65 through 80. And these would represent IP addresses that are routable over the internet. Now, as a company, we aren't just going to pick these nilly-willy out of the air. These are IP addresses that are associated with our company. So the entire internet and the routing on the internet would have to realize that this IP address space is all belonging to this company right here, Acme Incorporated. So that way, if a server on the internet ever needs to send a packet to 23.1.2.67, 68, 69, 70, etc., the internet's going to route that traffic over to our service provider, who will then route it back over to us, specifically over to R2. And here's the game we play with NAT. When Bob sends his packet that goes through the network and it hits R2, R2 is going to say, oh, I realize based on the rules that have been set up, I need to perform network address translation. So if Bob's source address is 10.1.0. Let's say it's 50, just as an example. What the router is going to do, it's going to swap it out and replace the source address with 23.1.2. Let's use the first IP address in this pool of 65. And then it will continue to forward that packet out to the internet. So now the internet sees this source IP address as 23.1.2.65 and not as the private IP address space. And the magic is that R2, this router right here, router 2 is going to remember that translation and keep it in memory. Why? Because if a packet ever comes back to the IP address of 23.1.2.65, R2 has to remember to untranslate that and replace the address back with the 10.1.0.50 so that it can be further routed all the way back into Bob. So that's what network address translation is all about. It's about swapping out an IP address from a layer 3 packet and replacing it with something else. In this example, we're replacing an RFC private IP address space with one that's publicly routable over the internet. And when we replace the source address, as we did here, so Bob's source address of 10.1.0.50 got replaced with the source address of 23.1.2.65 for that packet's journey over the internet, they refer to that as source NAT because we're replacing the source address. In this example, Bob's computer's source IP address was replaced with a globally routable IP address so it could be sent over the internet without being blocked at the service provider. So we might also infer from that, if source NAT is swapping out the source IP address, then destination NAT is very likely swapping out the destination IP address. And that's exactly what that is. And a scenario where we'd use destination NAT is this. See this server right here? This public-facing server, server number 1? Let's say it has the IP address of 10.3.0.99. That's the IP address it has on our DMZ. Now, that IP address of 10.3.0.99, it starts with a 10. It's in the RFC 1918 private address space. That's not routable over the internet. So how is Lois out here on the internet going to be able to get to that web server? And the answer is we're going to set up destination NAT. So here on R2, once again, we could go ahead and say, let's use 23.1.2.80. So we'll change the range of the NAT pool, and we'll use 23.1.2.80, which is still allocated to us, to our company, as a globally routable address. What we'll go ahead and do is have R2 map that IP address over to this internal IP address of 10.3.0.99. So now when Lois is sending a packet to 23.1.2.80, that packet will be routed to R2. R2 will see that destination address, and because it's configured with NAT, and R2 is also configured with a rule that says we're doing destination NAT, R2 is going to change this IP address, 23.1.2.80, over to 10.3.0.99, and then continue to route it inside our network. So in that case, the firewall would get it, and then the firewall would route it up to the final destination, which is this server number 1. Or if we were using a load balancer, we could have an internal load balancer using a private IP address on the inside, and then have a globally reachable address mapped to it on the outside using destination NAT. So Lois would go to 23.1.2.80, and if that global address was mapped to an internal address of this load balancer, we'd have a very similar result, except this time the packet would be routed to the load balancer, which could then load balance across multiple servers on the back end. Now, one of the big challenges with doing network address translation is that usually, especially for small companies, they don't have a pool of globally routable IP addresses that they can use to perform network address translation on. In fact, for many small companies, they may only have a single IP address that's on this router interface right here that allows that router to connect to the internet. And maybe this was assigned via DHCP from the service provider. Or perhaps the service provider told us specifically what IP address to use, and that's what we're using. So let's say we have the IP address that ends in .253. And for our discussion, let's say that that IP address is a globally routable IP address on the internet today. Now our problem is we have users like this user and this user and this user. And the challenge is if these users whose network address all begins with a 10, which is the RFC 1918 private address space, how do we get them out on the internet if we don't have a whole pool of IP addresses to use for individual devices to get a one-to-one network address translation as those packets go out to the internet? And one solution would be to use PAT, Port Address Translation. And port address translation is amazing. It's also sometimes in a Cisco environment referred to as overloading. And it goes something like this. Bob's computer sends a packet out to the internet. It hits this NAT device, R2. And if router 2 is configured to operate as a network address translation device using PAT, PAT really is just a subset of network address translation. We're still swapping out an IP address. And with PAT, what the router is going to do, it's going to go ahead and put whatever that first 3 octets are, .253 with the global routable address. So from the internet's perspective, it looks like Bob's packets are coming from the IP address that's been assigned to the interface on router 2, a single IP address. Now, what about another user like Laura? Let's say Laura is sitting at computer number 1. She also wants to go out to the internet. Let's say she has the IP address of .51. So Laura's source IP address is 10.1.0.51. And once again, the router, if we're using PAT, will change that source IP address and change it to the first 3 octets of whatever is on this interface, .253. So Bob and Laura's traffic, as it goes out to the internet, are both going to appear as if coming from .253. Now, one of the challenges is, if Bob is going out to the internet and Laura is going out to the internet, it's very likely we're going to have replies coming back from the internet. So those replies, as they come back, router 2 needs to do a very good job of keeping track to make sure that the correct response goes back to the correct client. And the way it tracks these translations using PAT is by also including port information. So with PAT, the router keeps track of not only the IP address involved in that session or in that conversation, but it also keeps track of layer 4 information, such as ports with TCP or UDP ports. And we'll talk more specifically about ports in a separate nugget, but for now I want you to be aware that it's tracking that additional information to make sure that when the response comes back, that this router 2 running PAT can correctly forward the correct response to the correct client. So for example, maybe Bob's source port was 13,000 and maybe Laura's port was 1875. That will also be tracked in the translation table on router 2 so that when the replies come back based on the ports involved and the types of traffic, the router can correctly send back the response to the correct client. And the benefit of using port address translation is we can overload tens of thousands of IP addresses of clients on the inside, for example, on a single IP address that's routable over the internet. And it's for this reason alone, the ability to do port address translation, which is a subset of NAT, that has kept IPv4 in business for over a decade longer than it really should have. And that's because as IPv4 has run out of address space, we can continue overloading tens of thousands of IP addresses behind one PAT address to extend the lifetime of an otherwise exhausted IP addressing scheme. So what I thought would be fun is a simple example. Let's go to PC number 2 here, which is running Windows 8.1. It's currently connected to this network. R2 is currently configured with network address translation. Specifically, it's using PAT, port address translation, which is a subset of NAT, and it's doing overload regarding the IP address on its interface 3/2. So all the customers here on network 10.1.0.0, as they send their traffic out to the internet, router 2 is going to translate the source IP address as well as keep track of all those sessions so that when the reply traffic comes back, it can correctly untranslate that traffic and forward the responses back to the right party. So here on Bob's computer, which is PC number 2, let's go ahead and open up a browser. And all I'm going to do is launch Chrome. It's going to Google's main page, and that's it. Because that was enough to generate traffic going out to the internet, including DNS, including this web page that we're looking at. And router 2 in our topology did network address translation to allow those packets to be sent to the internet and also allow the correct return of that traffic to Bob's computer. So here we are on router 2, which is the perimeter router between Acme Incorporated and the internet service provider. And if we issue the command show IP NAT translations, it's going to have all the translations that are currently in the table on this router. Now this is an example of a Cisco IOS router, and the command on a different flavor of router might be slightly different. And the point I want to drive home is that this router is doing network address translation, and specifically the subset called PAT, port address translation, And because we're doing translation of source addresses, it could also be referred to as doing SNAT or SourceNAT. So here is the inside computer, which was 10.1.0.101. And even though I only opened that one browser, there was just a ton of different requests to populate and fill that browser. And what I'd also like to point out are these are the ports involved. So as Bob's computer chose some ports to use for the individual sessions, port address translation is tracking those. And on this router, it's also changing those source ports to the source ports the router wants to use for the PAT. So 10.1.0.1, which is the IP address on PC2 that Bob's using, got translated to the address that ends in .253. And in my lab environment, I also happen to be using an RFC19 address space on that outside interface as well for this PAT process. And that's not atypical. Service providers often will use for the first couple of hops till you get through their network. They'll often use RFC 1918 addresses as well for the customer edges of their networks. In this nugget, we learned that network address translation is all about swapping out an IP address at layer 3 in an IP header. If we swap out the IP address on behalf of one of our clients that's going out to the internet, that's referred to as SourceNAT because we're replacing the source IP address. If a client from the internet is trying to hit one of our servers or connect to one of our servers, they would be connecting to a public IP address, which we would be swapping out for an internal address for that destination server. And that's an example of destination NAT, where we're swapping out the destination IP address in the header before we continue to forward the packet. And because we don't have enough global IP addresses for every computing device on the planet for IPv4, we use port address translation, which allows us to overload a single global routable address with tens of thousands of IPv4 private addresses per global address. And that subset of network address translation is referred to as port address translation because it's tracking the port information. For example, the TCP or UDP port information in addition to the layer 3 translation to make sure that the replies for each of those requests goes back to the right individual on the inside network. I am glad that you joined me for this nugget. I hope this has been informative for you, and I'd like to thank you for viewing.